Now let us start with the second group of S block, that is the alkaline group. So let us focus on the members of this group first. So it includes beryllium, magnesium, calcium, strontium, barium and radium. And the symbols for them are written on this side. As you can see, beryllium is Be, magnesium is Mg, calcium is Ca, strontium is Sr, barium is Ba and radium is Ra, right. So you know that why they are called as alkaline earth metals, because the first question is that you should know that why they have been given a special name, that is the alkaline earth metals. The reason is that they form their oxides and their oxides are alkaline in nature. Moreover, they are not attacked by the heat, they are not attacked by the fire, they remain in the earth crust. So this is what the reason behind that they are called as alkaline group members. So the first property we are starting with them is the function, the configuration. So the first focus is on the atomic number. As we know that beryllium's atomic number is 4, so particularly its configuration is helium-2, 2s2. As we know that general configuration is going to be ns2. So that means their last orbital is going to be the s1 and in which the maximum 2 electrons are going to present. So for magnesium it is 12, so it is neon 3s2, calcium argon 4s2, strontium krypton 5s2, barium xenon 6s2 and radium is radon 7s2. As I have wrote in a compressed form, you can write in an open form also, that both are the same thing. So now we are going to, as we know the configuration now, they all have ns2 electrons. So now we are going to start with the other physical properties, that the first property is atomic radii. So like if I compare them with the first group, as we know that first group is lithium, sodium, potassium, rubidium, cesium and francium, right. So we are going to compare them with the first group as well, and we will compare their members among themselves also. So as we look for the atomic radii, we have seen that alkaline group metals, they are actually smaller. They are smaller than alkali metals. They are smaller than alkali. Why? Because in alkali you can see that here the configuration is ns1 and here the configuration is ns2. That means an electron is added to the same shell. An electron is added to the same shell, and we know that when an electron is added to the same shell, so that means the nuclear charge will increase and the size will shrink somehow. So that is why the alkaline group members are actually smaller than the alkali one due to increased nuclear charge, right. And if we compare the alkali metals among themselves, we see that out of them beryllium is the smallest one. As you can see, it has 2s2 shell, it has the shell still third, it has shells till 4th, 5th, 6th. So every time a new shell is being added, as you can see with the configuration. And we know that whenever the shell is added, so that means nuclear charge is also increasing and the screening effect is also increasing. But here the screening effect actually overweighs. So that means the effect of the screening effect is more pronounced, due to which the size is increasing. So we see that in the alkaline group, the beryllium is the smallest one, and every time the shell keep on adding, due to which screening effect increase, therefore the size also increases. So that means along group when we move, size increases because nuclear charge decrease and shielding effect particularly increase, right. So this is what is the atomic radii. Now coming to the second property, that is the most important property, that is the ionization energy. As you all know that ionization energy is that, suppose I have a nucleus, I have a shell and I have electron in it. So that means if I want that this electron, if I want to remove it, I have to supply it with certain amount of energy, and that energy is particularly called as ionization energy, means amount of energy required to remove most loosely bound electron from outermost shell of an atom. So if we compare the ionization energy of the alkali and the alkaline, let us say this is for the alkaline and this is for the alkali. So if I need to compare them, so what we will see that here in alkali the configuration is ns1 and here the configuration is ns2. If we talk about the size, they are bigger and they are comparatively smaller because they are high nuclear charge. So that means ionization energy of alkaline is going to be greater as compared to the alkali, right. And now if we compare their second ionization energy, for example, I will take an example. Suppose I have sodium and I have in contrast I have magnesium. So I know that it has 11 electrons. So let us write the configuration first. So this is the configuration, and for magnesium it is particularly this thing. So that means, as you can see that here the size is bigger and the size is smaller, and as far the stability is concerned, it is somehow stable because it has the orbital filled, completely filled. So that means its first ionization energy is going to be greater as compared to the first ionization energy of alkali metals. So now, but after the removal, what happened? We have configuration this, and here we have configuration this. So now in this case, it has acquired actually a stable electronic configuration, 6 electrons in p subshell. So that means here the energy required will be comparatively more high as compared to this. So that means second ionization energy is lower than the this thing. It is more for the alkali metals, it is less for the alkaline, because here you are going to disturb the stable electronic configuration for the alkali metals. So this is how you compare alkali and alkaline ionization energy. And as far if we talk about the group, so as we know that beryllium is on the top and barium is at the bottom or followed by radon. So we see that every time when we move, size increase, nuclear charge decrease. So that means obviously there is less force of attraction, the electron is facing from the nucleus. So that means ionization energy will particularly decrease, right. So this is how we are going to compare the ionization energy. Third we have is the hydration energy. We know that smaller is the size, more easily it is hydrated, and more it is hydrated, less is the mobility. We already discussed in the S block also, this thing, the first group also. So we have seen here that if we compare them, so beryllium is particularly is going to have, it will be more hydrated as compared to magnesium or as compared to calcium or as compared to strontium, or it means rest of the member. That means as we go down, we know that size is particularly increasing and the hydration power is somehow decreasing. So that means maximum hydrated will be beryllium, and after that when we move, size keeps on increasing, due to which the hydration energy produces comparatively less. But when we compare hydration energy of alkali with alkaline, so we have seen that alkaline is somehow smaller. Smaller means they will be maximum hydrated. So that means they are hydrated more as compared to the alkali ones, right. And as we go down, as we move in the alkaline group, the hydration energy is somehow decreasing because the size is somehow increasing due to decrease in the nuclear charge. The next property we have is the electropositive character. What is that? We know that electropositive character means tendency to lose electron. It is tendency to lose electrons. So we know that as it has, it is a metal and it has this thing configuration Ns2. So that means they have tendency to lose electrons and form electropositive ions. And moreover, the reason behind is that they have low ionization energy and big size. So that means they are electropositive, they will lose electron, they have tendency to lose electron, and after that they will be forming electropositive ions. If we talk about the electropositive nature in the group now, so we know that it will be comparatively less electropositive, and the electropositive character will keep on increasing, because as we move down, size is somehow increasing, nuclear charge is decreasing, and ionization energy is further decreasing. And when the ionization energy is decreasing, that means the electropositive character is increasing, because tendency to lose electron is more, and for that you need to supply with a small amount of energy. So this is how the electropositive character increase down the group. Now we have seen that we'll see that whether they have tendency to form dipositive ion or they have tendency to form monopositive ion. Suppose I have beryllium. We know that particularly it has 2 electrons in s orbital. So we'll say that it will lose 1 electron, let's say, and it will form a positive ion. And if it will lose one more, it will form Be2 positive ion. So we have seen that they have more ability to form dipositive instead of forming monopositive. They have more ability to form dipositive ion. The reason being, after removal of 2 electrons, as you can see here, after removal of 1, they have not acquired a stable configuration. But after removal of 2, if I remove this also and this also, they will acquire a stable configuration. So that means they will be forming a di-positive ion, because di-positive ion after losing 2 electrons, they will somehow require a stable noble gas configuration. This is what they need actually. And moreover, the reason being, the di-positive ones, they often exist in solid state because they are too small in size. More is the positive charge, we know that smaller is the cation. So that means they are smaller in size, they can fit better into a crystal lattice, and that is why they exist in a solid state. And moreover, we know that like if we have beryllium positive and we have beryllium 2 positive, which is going to be smaller in size? Obviously this is going to be smaller in size, and more smaller is the size, we know that more hydrated more hydration energy will get, or it will get maximum hydrated. So this is the reason that the alkaline earth metals actually form a di-positive ion, not because they have, after forming this di-positive ion, they acquire somehow noble gas, their size becomes too small, that can fit better into a crystal lattice, and moreover they get maximum hydrated. So that is why the di-positive ion is much favored. But if we compare the positive character with the alkali metals, we see that they are monopositive because they have only 1 electron, and after removal of 1 electron they will acquire these things, that means the stable noble core, so that means or you can say that their ionization energy actually increase. So in that case unipositive ion is more stable, and in this case di-positive ion is more stable. Now coming on to the next property, melting and boiling point. We know that smaller is the size, more is the intermolecular bonding, and higher is the melting and boiling point. So if we compare their melting and boiling point with alkali ones, we know that they are actually smaller. So smaller means they have high melting and boiling point, right, as compared to the alkali one, because they are of small size. But as we move down, we see that melting and boiling point gradually decrease due to increase in the size. But you can say decrease is not occurring in a regular trend. But still it possesses the high melting point. That means the one which is on the top is going to have high melting and boiling point. But as we move down, melting and boiling point gradually decrease. However, the trend is not uniform, but still it is decreasing. Next is the density. So out of alkali and alkaline, what do you think, like out of them, which is going to be more denser? Obviously alkaline is going to be more denser, because we know density is mass per unit volume. So as alkaline are smaller in size, they will occupy more mass in a given volume, and as compared to alkali or in alkali they are bigger actually, so they will occupy less mass in a given volume. But as we move down in an alkaline group, we see that size is increasing, therefore density is decreasing. There will be less mass in a given volume. Likewise, we have another property, that is flame coloration. As we know that they have, like if we talk about their ionization energy, so in general if we talk about ionization energy, actually they have low ionization energy, because this is the second group. The biggest group is the alkali group and the second biggest group is the alkaline group. So if we talk about the general form, we are not comparing with the alkali, we are comparing in the whole periodic table. So this is the group which possesses the second number, which falls on the second position if we talk about the lowest ionization energy members. So that means energy of the Bunsen burner is sufficient to excite an electron, and that is why we get a color of the flame. But one important question, you know that out of them beryllium and magnesium do not impart any flame color. The reason being, they are too small in size and their ionization energy is too high as compared to rest of the members, that the energy of Bunsen burner is not sufficient to excite an electrons or impart a color to the flame. So rest of the members, they do give color. So if we talk about calcium, you know that color obtained is something we call it as crimson, right, and likewise it shows apple green color. It is again crimson. So this kind of colors actually they show when we supply it with Bunsen burner energy, they get excited to the high energy level, and it remain there for certain period of time, and then when it comes back, it just radiate the energy absorbed by it, and that energy falls in a colored region. So that is why it is actually imparting a flame color, but beryllium and magnesium do not, because they are too small, their ionization energy is too high, or you can say the energy of the Bunsen burner is not sufficient to cause an excitation. Now the next property is reducing nature. So if we talk about the reducing nature, they do have tendency to lose electron. We know that any substance which has tendency to lose electron act as a reducing agent. So they do have tendency, but their tendency is comparatively low as compared to alkali because they have high ionization energy. So if we talk about reducing nature, their reducing nature is they are weak reducing agent as compared to alkali ones. But as we move down, the beryllium is an exception because it has less tendency to lose electron, right, because it has a smaller size. But as we move down, we have seen that every time a size is increasing and electropositive character is increasing because ionization energy is decreasing, therefore the reducing character is increasing. So that means in this as we move down, the reducing character keeps on increasing, or it keeps on becoming less more negative, and we know that when the value of electrode potential is more negative, it means it is stronger the reducing agent is. So this is what we actually observe. So I think it's clear with the physical properties that if we talk about atomic radii, they are like in comparison to alkaline, they are smaller. Ionization energy is comparatively higher, and hydration energy, they are less high, they are more hydrated actually because they have small size than alkali. They have tendency to form dipositive because after that they acquire a noble gas core. They are less electropositive because they are of small size. Their melting and boiling point is quite high as compared to alkali because they are small size. More denser because they are small size. Flame coloration, yes, they do have, but beryllium and magnesium do not impart color because they are small in size. Otherwise the rest of the members they impart. Reducing nature, weak reducing agent as compared to the alkali ones. But still if we talk about the group, we see a lot of variations because we see that out of them beryllium is going to be very small with highest nuclear charge and the highest ionization energy. But as we move down, the size is increasing, ionization energy is decreasing, electropositive character is increasing, and a lot of things were found in the group, right. So this is what is the physical properties. Now